We develop in our lab solutions involving digital forensics, machine learning, and reasoning for complex data to these kind of problems. And today I separated 3 explorations of interest for this workshop. These 3 explorations, they have names. The first one is a project that we have called Deep Eyes. Our idea here is to receive a document, be it a text or a photograph or a video, and identify if it's fake or real. And then, if we can do that, we also want to check how it was created, source. So it's a problem called source attribution. The second project is this one. This is a partnership with DARPA in the US. And our objective here is not only analyzing the object itself, but how this object relates to others. So if you think like an image that goes online, you want not only to verify if this image is fake or not, but you also want to chase this image wherever it goes and to create the phylogeny tree of this image. So if someone goes to Facebook and publishes like a fake photo of someone, we want with this project here to identify if this image is fake. And with this project, in a collaboration with DARPA, to check how this image was spread all over the internet. So if another person comes in, modify that image and publishes it again and reshares it, we want to find that link. We want to find that this modified image is a child of this original image. And then if someone else goes there and gets this child and modifies, like rotates or creates or puts another person in there, puts a face in there, we also want to find that relationship and create this graph of relationships. So with that, we are able to detect fake content and how it was spread. And then when we unite these 2 things, we go to the project that we have, that we want to start now, that's called Deja Vu. Deja Vu, the idea is to reconstruct an event. What happened, how it happened, and who participated. So, let's see a little bit about this. Deep Eyes, it's a partnership with UFMG and the Brazilian Federal Police. And the first thing here is to get a bunch of data, normally multimedia data, and to check which one is real, which one is fake. If it's a fake photograph, how it was created, if it was created in Photoshop or GIMP or something like that. If it was a video, how it was created, where is fake and where it was forged. And we move to the next step, which is checking the source. So checking the source is this. When you get a document, you normally need to find out how it was created. Which one was the camera that created it? Which one was the printer that printed it? Why is this important? Because if you're talking about an apprehension, of $100,000 in the premise of someone, if you can link that fake money to the printer, it's a whole new thing. So here, given a printed document, we want to identify which one was the printer that printed it. Given a digital photo, which one was the camera that acquired it? So this is a problem called camera or sensor attribution. And then, of course, we go to the problem of identifying human. So human identification. We can do that through a series of biometric traits. One of them is face. And here we have some research to identify 2 persons based on these biometric traits. In this example, we have a solution, we are developing a solution tied to social media in such a way that we deal with heterogeneous data and big data, and our idea is to identify who was involved, who was present in that picture that we analyzed. As I mentioned before, this project, Deep Eyes, has the objective of dealing with isolated objects. It does not try to find relationships. So another thing that we do here is, given a CCTV image, we try to, and if it's like from an automobile, we have a serious problem with the Federal Police, which is trying to identify the vehicle. And to identify the vehicle, you need the license plate number. And normally, the conditions of acquisition of those plates are very bad. As you can see here, this is an example of a vehicle trafficking in a traffic in Unicamp, and how we could get with a normal extraction was that. And here we want to go a little bit further and to come up with something like this. This is the result of a PhD thesis of a student of mine that just graduated. He received images like this, and after his research, he ended up with something like this. So this is something that our algorithms of machine learning can learn later and can automatically detect and tell us which is the character in there. But this was pretty much impossible. So using visual computer vision techniques, he did all of this work to come up with this. And then with some machine learning algorithms later on, we received this as input, and we were able to point out an average of 6.5 characters correctly. Remote sensing, again, isolated objects. Our idea here is to learn a little bit of some content of interest. In this case, a partnership of, I think, 3 years already with the Federal Police. We are monitoring plantations of marijuana from satellite images. So our idea here is to receive an image from a satellite like this one and pre-process like that image to come up with something like this. And with this representation here, we developed some algorithms to automatically separate marijuana plantations from other normal plants or non-plants. This is ongoing. Pretty much all of these projects here are ongoing. Okay? None of them is finished. And complementing the face recognition algorithms that I mentioned, we also have some based on behavioral biometrics. This one based on how a person walks. All right, so we go from the project that focus on isolated objects to the project with DARPA that tries to find relationships. So now things get a little bit more interesting. This is a partnership with DARPA, Purdue, Notre Dame, Politecnico di Milano, NYU, and Unicamp in Southern California. Here is what happens. We receive as input a series of images or videos and a query. Suppose that you receive as a query a photo of Osama bin Laden being killed. So this is an example. And you think or you hypothesize that this image, this photograph is a fake. So how was it created? How did it spread online? So these are the questions that you want to answer. So we start with doing some forgery detection analysis. We try to identify the region of the word. It was acquired using ENF analysis. I don't know if you are familiar with this, but using the frequency in the electrical power sources, the power sources, you can have an idea of where an image or a video was created. And we do some sensor attribution, and with that we can start measuring and comparing pairs of images and pieces of pairs of images, like subparts of images, to come up with this graph of relationships. So to put more in details, what happens is something like this. We have a collection. We represent all of this collection using some descriptors. This is big data, so you're talking about millions of images. And when you have the query, you need to go to this database. And we have a series of tiers. In each tier, we try to solve a part of the problem of the search, because this is time-consuming. And then when you find some context in the images that you are retrieving, you put them in a more confined word, and then you can repeat the query with some other high-related images that you find. So here's an example. This was an example created by NIST, the Standards Institute in the United States. We call it snail eating cucumber, just as an example. You have here the snail and the cucumber. And this image here was modified with some illumination changes. Here we added some shadows. Then here we got like a wallpaper and put this nail here. But the wallpaper came from this image. And then when you add these two together through overlay, you can also do some re-illumination to make it more believable and so on and so forth. So the question is, when you start now with any of this as your query, how can you find all of the others? This is the question DARPA wants us to answer. So suppose that you start with this one. So you can find that it's fake, because you do some illumination analysis, some shadow analysis, DNF, and then your solutions say, your solutions point out that this image is a fake. Okay, it's a fake, but now I want to know how it was created, how it spread online, and the parts that have been modified. So doing this phylogeny analysis that I'm mentioning, we go now and decompose this image in several parts of the forgeries. And then we come up with this part here, this nail, this part here, these people, and other parts. And for each one of them, we do like these partial queries. And then when we find all of these related images, for instance, this one was created using those pieces there and those pieces, we do the relationship of each one, each pair of them, to come up with this graph. So this is what we want to do in this project. It's a project that we have been running for 1.5 years already, and we already are able to deal with like batches of 1 million images each time, and we have a solution that can identify these relationships with about 70%, 70%. But it's getting better. So now, put all of this in context to identify and interpret actively an event. So this is a partnership with more universities because it's a big project. It's just starting. It's a thematic from FAPESP. I'm the coordinator. Professor André here is a co-coordinator of this project. It's a partnership with ICMC, UFMG, Purdue, Notre Dame, Politecnico, Siena, Warsaw, and Singapore. And here is the main picture of the project. We start, as in the DARPA project, we start with everything that you can collect from social media. So you have something that happened. Unfortunately, this is not surveillance. The problem already happened. Now, the best you can do is try to understand what happened to avoid it in the future and to identify who participated to properly chase them. So here is the social media. You collect all the information that you can about it. It can be from CCTVs, it can be like keywords, venues, time period that you have. And once you get all of this is continuous, so it's an information that keeps coming. And some of them keeps missing. Some of them appear and disappear, and so on and so forth. Then you go to the second part of the project, which is the data organization. Here we want to know the time that we are talking about, where we are talking about, site information, which places of interest that we have in this data, objects of interest like a bus. Someone got a truck and used this truck to hit some people in a region of the city, so you want to find this truck in different images and videos and track it. You also have an approximate time of what happened. Suppose it was 1:05 p.m., so you want to find everything that was closely related in time. So it started at 12. At 12:05, someone got the truck, and at 12:10, this person arrived, and at 1 p.m., it burst. So we want to put everything in time and organize it. And then we are going to do the X coherence. So we need to relate in time and space posts, texts, images, and videos. And then we want to create a timeline of what happened. If we are able to do so, we can go to the next step, which is analyzing. Trying to find the most frequent person or persons or objects. Try to isolate them, so finding persons and objects and places of interest. Try to see if the images or data that we received are fake or real, because suppose that you're talking about an event that just happened, but all the data that you collect are fake. So This is very common. Recently we had the case of the hurricane, and whenever we have a big event like that, a lot of people go to the internet and they just get images from other times, modify it, and post in social media just to have publicity, just to have the attention of other people reading their posts. So when we try to understand like the deja vu of something that happened, we need to be aware of fake contents as well. Alright, we are talking about big data, of course, because this is like not a robbery in the corner. We are focusing on big events. As we are focusing on big events, one of the main questions where we can have profound contributions is how to synchronize these different sources of information. We are kindly calling this X-coherence, so we invented this term, because we're talking about feature, space, and time coherence. How to do this efficiently? Because if an event just happened and you need like a year to do that, it's very complicated. So you need to do that fast. How can you extract and mine information of interest, pattern discovery, and how to filter specific aspects of this process? Of course, you also need to rule out spurious data. One PhD project just starting on this is this one. It's called Finding the Arrow of Time. I give you two images. It's a pair of images. They are from the same place. The PhD question here is, which one came first? Just that. You cannot use the meta information just based on content. Which image came first? And of course we can do that, at least to some extent, because the sun moves from one day to another. And within the same day, you also have some shadow changes. And then when you can calculate those things from images, we can try to solve this question of which one came first. Here's an example. This was in the 60s. This was in the 2000s. If we can train a solution to differentiate human-made objects, we could say that this one came first, this one came second. But of course, if we're talking about the scenario of a war, this could very well be the first one, the second one, if we had destroyed this one. So there are some nuances that we need to focus on. As I mentioned, we are talking about social media as a source of information, understanding what's there. We need to understand as well who published this kind of information, and we want to discover patterns. So here, I selected some examples of where we can get. We prepared these just to show that it's possible. So it's a case study from 2013. This one was made by my group and the group in Politecnico di Milano. Here we had the objective of reconstructing the moment, the very moment that the bombs went off. So it's called Who's My Parent, because we wanted to find the different shots. So let me explain what's going to happen here. We collected everything that we could from social media, but only videos from this event. And of course, we had different points of view and different moments in time. And we wanted to create a notion of a person that was walking in there. It's a virtual actor. And then all of the cameras would automatically change to the point of view of that person. So suppose that it started here, one camera, then this person starts walking, this camera cannot have this view anymore, so automatically our system changes the point of view to the next camera that can see what happened and so on and so forth. So in the end, we integrate several cameras to have one view of the event. So we start going to YouTube, one of these sources that we use. We collect the videos from cell phones and CCTVs, everything. We put them in the pool. And then we For each pair of videos we match when they are talking about the same point in time. So here the video already started, then a second one comes in, and now they are talking about the same moment. So they are aligned here. So this part is not of our interest because we could select just one of them. But the moment that one of them finishes, it's of interest. So I would use that point of view if necessary. So here's another point in that these two videos have the same point of view, same vantage point. They have different sources. That's a cell phone. This is a BBC footage. We also did this as an example for the meteorite that hit Russia in 2013. Same thing, we align the videos. Then the question is where we can get. We want to get here. Videos come in different times from different points of view, different sources. They finish at different points. We align all of them. And then we create the sequence of these virtual actors. So this is one. So this one started with like actor 1 from channel 5. So it's moved already to another one. Third one, so you have a smooth transition from sources to sources, and you have this notion that you are walking through the event. So this is what we wanted to do. Here's another example. Another example. This is from BBC, first video. Everything is okay. Then the first bomb went off. Now it's a second viewpoint. The person starts walking. And then, look, this person is getting up. Then it moves into another view. So you have this smooth transition from one camera to another. And you have this nice view of what happened. And from here, we want to extract patterns and identify the most important aspects of the event and come up with possible suspects. This is what we want to do. I don't know if it's going to be possible. We have 5 years to do so. And we need partners and collaborators to do that. All right. Just to finalize, 1 more minute. I'm going to skip this example from Las Vegas shooting, and I'm going to get another one, the last one, from a group in London. This is the attack of Israel on Haifa. It's called Black Friday. So this was done not using machine learning. This is not my group, but you are going to get the idea of where we want to get using
what these Reading military did and why they did it has formed the basis for groundbreaking investigative collaboration between Amnesty International and Forensic Architecture at Goldsmiths, University of London. It provides an unprecedented levels of detail what happened that day, in depth and breadth that's unmatched.
In this case here, they use satellite images as well.
It reveals evidence of war crimes and possible crimes against humanity.
Using hundreds of images and videos. I'm using satellite imagery, the accounts of mainstream media. We're using testimonies collected by Amnesty International. We're using accounts of Israeli soldiers. And what is necessary to do is to build a 3D model and locate each one of those various media in space and time. The aim is to reconstruct hour by hour, minute by minute, every event that happened during this first Black Friday.
To help establish the time it took place, forensic architecture
They did this by hand. They are architects, not computer scientists. We want to do this with machine learning.
Imagine we build the entire city so that we can get the shadows right and match every shadow that we see in a photograph with a digital shadow that we can simulate in a computer. So that 3D model of Rafah as a sundial allows us to time every photograph in which we see the shadow mark.
Now knowing the location of the bombing and having confirmed the time it took place, forensic architecture then started examining the type and size of weapons dropped.
Have acquired a video that is quite a rare instance where you see the bomb in midair.
In this case, they were able to isolate the missile. And with that,
We are able to analyze from the shape of the bomb, the type of bomb that was used.
they calibrate and they find the kind of missile that was used. They did this in the time span of a year. We dream we could help in situations like this with much less time. So we are looking for partners for this kind of research that I presented here, and also possible sponsors. My contact is here. This is the contact of my lab. And I think that's it. We have like 1 minute for that. Okay.
Of care or precaution do you take to prevent these being used against your goal?
Very good question. Well, this is like an arms race, right? When you have your algorithm out there, I cannot prevent other persons to come and use your algorithms to understand what you're doing and do their job better. So suppose that I have a forgery detector here that's based on illumination. I cannot prevent forgers to go there and use that algorithm to like create a forger and try to deceive my algorithm. Unfortunately, it's not possible. But it's like that's why it's an arms race. So whenever we do something, they do another, and then we try to fight them again in the other fronts.